or you can wherever.
This should I put
Oh, somewhere.
somewhere? Is it fine?
Recording in progress.
Okay, so I would like to thank the organizer for the opportunity to give this talk. So as Didier said, I will talk about the Compton scattering and positron annihilation spectroscopy and how they were implemented and the results we obtained in by the KKR Green function method. Okay, thank you. Okay, can you hear? Can you hear? Oh, maybe it's. Try it like this. Maybe it's better or. Okay. Yeah. No, it's not working. This.
Yeah, I have now.
One has to switch the cursor to another window.
Yeah, but it's a different screen.
Maybe you get out first and get in.
What it's. Okay, it's going up. Okay, I want to stress that, well, this work I started during my PhD stage at the University of München, so in this building, so in the group of Professor Ebert under his supervision and guiding. But this collaboration we continue a long time after I returned at my home university here in Cluj-Napoca. I want to also to acknowledge the collaboration we had with, so it's not individual work, it's a collaboration with many people. I would stress the contribution of Jan in the introducing the effect, the correlation effects by LSDA plus DMFT into the KKR code, which were quite important into our description, and also the collaboration we had with.
Sorry, Diana, we have to because we cannot hear it. We have to put it somewhere closer to you.
I have to take it in my hand. Okay.
Yeah, that would be the easiest.
Okay. So yeah.
But put it closer because you are speaking not so loud, you know, and that's.
Okay. So where I was acknowledging the collaboration with Liviu Chioncel at the University of Augsburg in the description of the electron correlation, which were you will hear much into this talk. Oops. I have to go down. Okay. So this is the outline of my talk. I will try to introduce the Compton scattering. I will give a short introduction. I will describe the theoretical framework, so the general one, and how it was implemented into the SPR-KKR code. And I will show some of our results with the magnetic calculation of magnetic Compton profile for these materials with iron, nickel, uranium iron 2, and iron nickel alloys. Some topics you will hear are the correlation effects into the Compton profile, so I will discuss, and low energy spin localization in the valence band of nickel. I will talk also about the anisotropy in the Compton profiles, and in the second part of my talk I will discuss about the positron annihilation. I will describe the theoretical framework and results we have obtained for this 2D Akar spectra, two-dimensional angular correlated annihilation radiation for nickel and vanadium. and I will try to sketch some conclusions. Oops. I will start with something that everybody knows about. It's a well-known effect, this Compton effect, discovered in the 1920s, Nobel Prize for that, as an inelastic scattering of the photon by an electron of the target. You know it, but from the formula derived to describe this effect, you do not see any influence of the target. So this formula is depending only on the scattering angle, and it's independent of on the nature of the target. So even if it's considered to be an early proof of the dual nature of light, so this is not all that can be obtained by this Compton scattering. Actually, the electrons, the target electrons, they are not at rest. They are moving. They form a distribution of the electron. They are in motion. So this Compton scatter beam is Doppler broadened. And in this way, it was proven that one can get information about the electron momentum density of the electrons in the electrons of the target. And this differential cross section has been derived in order to prove that, and by Klein and Nishina. Here you see only universal constants. Here is the incident energy of the photons and the energy of the scattered photons, and some about the geometry of the scattering. But what is important is here is this J of Pz, which is the so-called Compton profile. And this is a one-dimensional quantity, but it's an integral of the density of momentum in the plane perpendicular to the scattering direction. And it's normalized at this Z, which is the number of the electron. That's why, by this derivation, this scattering is sometimes called scattering on the charge of the electrons. And some very comprehensive description we can find into these papers. Going further, considering the polarization of the photons and the spins of the electrons on the same footing, so this another scattering cross-section has been derived, where a part of this term, which is the so-called Char scattering, it's another one which it's considered to be like a perturbation because of this very small tau. Here is a incident energy of the photon, here is the rest energy of the electron. And this couples the circular polarized beam, as I said, with the spin of the electrons. And this type of spectroscopy began to be important after the development of the advent of the synchrotron sources, which allow to obtain high energy photons and were able to increase this ratio and to be able to extract information about this term, which is called the scattering on the spin of the electrons. So this is the experimental setup. So by using circular polarized photon and by inverting the magnetization, one could record these differential cross sections, and subtracting them, one get information about what is called here the magnetic Compton profile of the electrons of the target. Or another way to get this information is to revert the hand of the circular polarization for the circularly polarized photons. And, well, you can see here the magnetic Compton profile, which is a integral of the density of momentum of the electron spin up minus spin down integrated in a plane perpendicular to the scattering direction. Here, some adjustments of the geometry can be done in order to maximize this cross-section in such a way that, well, the magnetization, it's aligned along the scattering direction. So this quantity can be seen as a one-dimensional projection of the electron spin momentum density along this scattering vector. And this is normalized at the spin momenta of the electrons of the target. The theoretical framework, as Hubert showed 2 days earlier, so is a standard SPR KKR approach we are using, so you find a code here. We use a full relativistic treatment of the electronic states using the Dirac equation. I should point out at this moment that, well, we have two kinds of approaches for treating the potential. The atomic sphere approximation, which assumes a spherical symmetric potential within a sphere, or one can use also the full potential approach with the space filling of the Wigner-Zeiss cell. The treatment of the correlation effects can be done also beyond the LSDA. By this implementation, LSDA plus DMFT and LSDA plus U, the first of one, the LSDA plus DMFT, imply complex energy-dependent self-energy, whilst the other is imply real and energy-independent self-energy. These were implemented in the SPR KKR code, and they are the multi-orbital interaction is parameterized by so-called average screen Coulomb interaction, this Hubbard-U term, and the Hund exchange interaction J you will see later on my presentation. And yeah, about these developments you find information in these papers. By using the standard SPR KKR Green's function approach, by this solving the Dirac equation, this Green function in real space is available for the spin polarized relativistic case, where we have here the regular irregular solution to the Dirac equation. This is the scattering path operator, and here is are the relativistic quantum numbers. But the quantity we are looking for, the density of momentum, it's of course in the momentum space, and when one should bring the Green function into the momentum representation. And this is done through this transformation using this eigenfunction of the momentum through this equation. Oops. So the eigenfunction of the momentum representation have this form, where these are some spinors. They obey this can be put it into this form, where we obey this equation, and by considering that, well, this function obey the Bloch theorem, and using the invariance, the translational invariance of the Green function, some delta can be obtained, because we have the spins, two spins ms and ms prime. We got a delta for it, and we have two momenta p and p prime, and we get a delta again. And the general formula for the Green function in the momentum representation we obtain is a bit, well, it looks a bit complicated. So it has two terms. So the first one, so these are T and tau matrices, and multiplied by this other matrices, which are overlaps of this eigenfunction of the momentum and the solution of the Dirac equation. But we can split it, this expression, into four terms, where here is the single side scattering, single side term, here is the back scattering, double counting to exclude, and a non-side diagonal term. Oops. Having this Green function derived, one can further integrate them into the energy up to the Fermi level in order to get this momentum density, three-dimensional. And to get the magnetic Compton profile, one has to integrate them in a plane perpendicular to the scattering direction. In the same way, one could get also the Compton profile, so describing this scattering on the charge, and one has to take care of all the normalization conditions, which in the case of Compton profile is at Z, number of the electrons, and in the case of the magnetic Compton profile, it's at the spin magnetic moment. So what the derivation, the complete derivation are described here. But what I should point out at this step is that, well, these two types of quantities, the magnetic Compton profile and the Compton profile, are describing the ground state of the electronic system. So this is a, how to say, particular for this type of spectroscopies. In the following, I will describe some of our results, magnetic Compton for iron and nickel. So after the implementation in this code, our code was done, we tried to see how good was our description for the magnetic Compton profile. So we had to see to put our results near an experimental magnetic Compton spectra, which was this one from Dixon. In order to be able to do the comparison, one has to broaden your spectra with the Gaussian broadening corresponding to the experimental momentum resolution, and to scale, of course, this profile at the spin magnetic moment of the target. So after doing that, so here is our results, this KKR spectra, and together with other calculations, some LMTO, FLAPW calculation, and experimental data. What you can see here is that at high values of the momenta, all the theories are describing quite well the experimental data, but differences appear in this low momentum region where the electrons in the physics and chemistry, electrons of interest in physics and chemistry are. So here are large differences between different approaches and experiment. This negative polarization in this profile we checked, and is due to the negative polarization of the SPD electrons, and we see some features here. This AB, which are due to the Fermi surface topology, and they are periodic. They are going also outside the first brilliant zone, so they are so-called Umklapp features. But we were so the agreement of our treatment with the experiment was good. Further, after the treatment of the electron correlation by the LSDA plus DMFT approach was implemented into the code, we could see the influence of this electron correlation into the magnetic Compton profile. Here is again nickel 001. This is the principal direction. This multi-orbital interaction by LSDA plus DMFT are parameterized by this average screen Coulomb interaction, this Hubbard U, and this Hund interaction was kept constant. So what we did, we just increased the value of this Hubbard term from 1.8 to 3.0 and see the effects of the electron correlation into the profiles. We see that, well, compared with the LSTA calculation, we get an improvement, mostly in the low momentum region, by increasing this U. But, this spectra should be scaled at the spin momenta, which are varying, which are decreasing increasing U. But at some points, having a too large value of U, this spectra goes under the experiment. So we could say that, well, the MCP magnetic Compton profile are improved by this treatment, and we can find the best agreement for the value of this Hubbard U equal with 2.3 volt electron. Similar work was done in nickel along other scattering principal direction, which are this 111 and 110, with the same conclusion that, well, in this low momentum region, this LSD plus DMFT treatment improved the description of the magnetic Compton profiles. In the case of iron, the study was a bit more difficult because we didn't have a unitary, let's say, experiment along different scattering direction. We should take it from different experimental measurements with different momentum resolutions. But, well, the discussion and the description was similar, but we can get improvement with LSD plus DMFT by including the electron correlation into the profiles. And this mostly we can get an optimal value for this Hubbard term, but there is also an exception here for the iron 001, where this DMFT treatment is a bit far from this experimental data, but these are much scattered. We treated also the electron correlation in nickel. We compared the effects of the static versus dynamic treatment. So this static treatment, as I said, is LSDA plus U approach, where with energy independent self energy. And what we have here is are the magnetic Compton profiles calculated, this blue line with LSD plus U, this red with the DMFT for two different values of the Hubbard terms. So this is 2.0 and 2.3. Together, yes, again with the experimental data of Dixon. We see that, well, if this U value is 2.0, one gets very good, not too big difference between the treatment of the electron correlation statically or dynamically. But this changes if this Hubbard parameter changes, and in this case the LSD plus DMFT improved. The agreement was the LSD plus U is worsened the agreement. I wanted just to switch and to show also the results for another system, just not to believe that, well, we treat our theory only for iron and nickel. So here is an Lave's cubic phase uranium iron 2, which is antiferromagnetic. We described the magnetic moments by the KKR LSDA, yes, and we found this spin magnetic moments in the antiferromagnetic coupling. So this is for the uranium and this is for the iron. Well, in the experiments, so the neutron scattering, they found for the uranium almost zero net, so total magnetic moment. So this orbital and spin magnetic moment, they cancel. Well, what want to point out that, well, our description is good in the sense of the getting a total magnetic moment close to this experimental one, but at that point we want also to check the magnetic Compton profiles of this uranium-iron compound, and we see here a huge effect of the spin-orbit coupling in this low momentum region. And if you remember, in this description of the Green function of the momentum, we had a non-side diagonal term which made us available getting the contribution from uranium and iron atoms, but we have to point out that, well, this non-side diagonal term gives us also interference term, so this is a mixed contribution coming from uranium and iron. We can here we can scale these contributions in order to get the spin magnetic moment, so about of the iron and of uranium. But I should point out that, well, this ratio between them is different from the ratio we obtain from the KKR, as this overlap matrices, this mixed contribution, is also important. Next topic I will discuss is the spin density localization in the valence band of nickel. So we started from the description of the valence band of nickel done by LSDA and LSDA plus DMFT, and it is known that LSDA plus DMFT improved the description of the correlation effects for these 3D electrons and gives the weight of the occupied bands of nickel properly and reduce the exchange splitting, and also reproduce this 6eV satellite in the valence band. As far as this spectroscopy which we described, so this magnetic Compton is related to the spin density, we just wanted to check, and yes, it's describe the ground state of the target. We wanted to check, well, if this feature is somehow seen in the Compton profiles of the nickel. And what we did was the following. So in the description of the magnetic Compton profile, we do all the time this integration, this energy integration. And of course we can split this integration into different intervals, and we could get some, so to say, slices between different energy intervals. We tried to interpret them, but it was quite difficult if you have many intervals, so we stopped with 2 intervals giving contribution to these magnetic Compton profiles, namely a lower part of the valence band, including this satellite, so this is up to 0.4 Rydberg, so this is the correspondence with the volt electron, and a higher part of the valence band near to the Fermi level. So we have actually this two contribution. This is from, in the case of the LSDA, LSDA plus U and LSDA plus DMFT. We have here, with this color, with contribution from the low part of the valence band, which includes these satellites. By LSDA, you see that this is just a small contribution. If we do the treatment by LSDA plus U, this contribution from the lower part of the valence band, which includes the satellite, it's increasing, it's larger and a bit broader, but quite large and broad contribution from this lower part of the valence band, including this satellite, we have if the treatment is done by the LSD plus DMFT, so those including the electron correlation effects dynamically. So what we know, we are in the momentum space, so what a large and broad contribution here corresponds in the real space to a localized one. So all these are related to the spin. So as we obtain similar behavior along other scattering directions, so here is the MCP along 1, 1, 0, we concluded, well, that yes, by this magnetic Compton profiles, we could say that, well, we have a spin density localization in the valence band of nickel by treating by LSDA plus DMFT and LSDA plus U treatment of the electron correlations. Another topic I will discuss are the correlation and isotropy in the Compton profile. So for this we just calculate the total Compton profiles of the targets. So, and we make this difference between the Compton profile calculated by DMFT and by LSDA. So here are we call them correlation and isotropy, this along this principal direction, and so they have this general formula. And also a second moment average second moment was computed in order to have a quantitative description for the correlation anisotropies. So here are the results for nickel 001 and the other principal directions. By increasing this Hubbard U parameter, we have an oscillatory behavior which with increasing amplitude by increasing this Hubbard U term. We could calculate these second moments, and these are also increasing by increasing this Hubbard U term. And we could find a sequence of these second moments along principal directions. So this for 111 is smaller than it's the smallest, but one have to take care that these are negative values, and absolute magnitude range is opposite. And we checked this correlation and isotropy from nickel against those of iron. So here we also calculated this second moments average, which we found to be smaller than those in nickel, and also this range is different between the second moments along different principal directions. If we use unbroadened profiles, Compton profiles, we have we were able to recover get also these umklapp features. So here, by these differences, which were seen in the magnetic Compton profiles, but only for this direction, for this for the 001 and 110. So along 111, we do not have. Okay, this second moment calculations relates with the expectation values of the kinetic energy, and also a bond average of the second moments of the differences could be calculated by this formula. This has to be divided by number of the bonds, and this is proportional, the average with the difference between the kinetic energy derived by DMFT and by the LSDA. We see that, well, this difference in the kinetic energy is decreasing as far as U is increasing, and this average value is this directional average is this dotted line, and we find agreement with that calculated by full potential LMTO. another topic which was discussed about the experimentalist and the scientists working in this field is the anisotropy in the Compton profile. So this is another type of anisotropy. We are looking about the differences between the Compton profile along different principal directions. Yeah, well, there are also experimental data here. So these differences have kind of oscillatory behavior, which, yeah, in experiment are these dotted lines. And what we obtained similar oscillatory behavior, but in all the treatments we have for the electrons, and the electron correlation, we have higher amplitudes. And of course, the differences between different theory appear at this low momentum region. We made this zoom up to momentum equal 1. And we got slight improvement by the LSD plus DMFT treatment in this region. Well, but these differences between theory and experiment we attribute to some possible non-local effects, which were not included in the description of our electron correlation treatment. Other subject I will discuss are the magnetic Compton profiles in some disorder and order iron nickel alloys. Here is the magnetic Compton profile along 001 direction in this iron nickel disorder alloy. Here are also experimental data from Kakutani. And of course, we could reproduce quite well these magnetic Compton profiles by including the electron correlation on iron with Hubbard term 2.0 and on nickel with 3. We wanted to check what happens with this profile if we apply these Hubbard terms only on iron and only on nickel. We saw that, well, here is the case when we applied it only on iron and only on nickel, and here only on iron. We see that, well, applying only on iron, they are, how to say, not effective. So we found higher correlation effects for the correlation which describes the irons, the nickels, sorry, here. If we go into more details with this profile, which is of this disorder alloy, you can find again these umklapp features, and by the decomposition we can do into this spectra, we can evidence the contribution coming from nickel and coming from iron. These are how to say, here we have also this interference term, but this is quite small compared with uranium iron 2. And, well, the ratio we have between the spin moments of iron and nickel is more or less like in the self-consistent calculations. What we can do more is to calculate the Compton profile for this order alloy, iron nickel. Even if the experimental data are not available, this type of alloy, it's obtained in extreme condition. Maybe you can find them in the meteorites. And by calculating them by order and disorder profile by profile for the alloys by LSDA, you do not find many differences between this order and disorder one. But important differences can be found if we use the LSD plus DMFT approach. And also if we, how to say, use this correlation treatment for this order alloy. So the differences between this, including the disorder or including the electron correlation, are, how to say, have comparable magnitude. Okay, so this was, how to say, our results, main results about Compton scattering. And in the next, I will try to discuss shortly and to, how to say, to introduce another type of spectroscopy which we studied, so this positron annihilation. So in the positron annihilation, we just treated the description of this 2D ACAR experiment, angular correlation of annihilation radiation, which is shortly sketched here. Having a positron source, a positron is sent to a sample, it's injected in the sample. After its thermalization, diffusion, it loses kinetic energy. At some moment, at some time, it's trapped. And annihilation between a positron and electron appear. And by this annihilation, two gamma quantum, two photons are created. These are, I mean, collinear, but due to this distribution of electron, there are how to say, not really collinear, and from this non-collinearity detected here, one could get information again about the electron momentum density as is seen by this positron injected here in the sample. The 2D ACAR spectra has this, how to say, expression, so it's the density of momenta for the spin up plus spin down, and here is integrated along only one momentum direction along this scattering direction of the photons. In the SPR Green function, SPR KKR theoretical approach, in order to describe this kind of spectroscopy, two-particle Green function should be calculated. So here we have the spins of the positron and of the electron, the momentum of the electron and the positron, and we can get this Green function in this momentum representation by this formula here with here with different Green function for the electron and the positrons. I should point at this moment that we work in the independent particle model, so we consider electrons and positrons to be independent particle, and under this assumption, so considering well that the positron it's thermalized, it loses the kinetic energy, so in the moment of the annihilation this momentum is zero, and it has a S-type band. He's at the bottom of the band. His energy of the positron can be calculated, and annihilation is done for the electron positron with opposite spins. If we input this into the Green function expression, one can get the expression of, and okay, making the transformation we showed also for the Comptons, we can get this Green function which depends only on the momentum of the electron and its energy, and integrating it through the energy of the electron, one could get this density of momentum spin resolved, and which is has to be introduced into this formula in order to calculate this 2D ACAR spectra. the experiments we checked, so here is the 2D Akar spectra. It looks like this for the vanadium, and here is our calculation. Well, we didn't use, so these measurements are done by the group in Bristol of Professor Dugdale, but at that point we only checked the correspondence between these two. So we were not going further, but quite later on we had, a collaboration with the group of Professor Hugenschmidt in the TU München for the measurements of this positron annihilation to the Akar spectra for the vanadium. And we were able to check the experimental data against the LSDA treatment and LSDA plus 2 and DMFT treatment for the electron correlations. Okay, maybe this is a difficult task, but well, what I wanted just to show is the differences by these principal directions. We have here some cuts of this profiles around 110 and 100 directions. We see the differences between the theory and the experiment in this spectra. And, well, the main differences appear at this gamma point. And, well, best agreement we have with the LSDA plus DMFT, but what was surprising is that LSDA gives better results in this gamma point compared with the LSDA plus U. But all this theory, so they somehow push this density of momentum away of the first Brillouin zone. In order to get information and to make the Fermi surface reconstruction, one has to do some folding and to put back this the points from this plane into the first Brillouin zone. This is done by so-called Lock-Crisp-West folding procedure. And the figure we obtain, so this under this diagonal is the experiment, and above is the LSDA plus DMFT results. So the agreement with the experiment we obtain is quite good. So we can say that, well, our calculation describe well the Fermi surface features of this for the nickel, namely this N-hole pocket and this jungle gym. So if here you have the projection of this Brillouin zone for the nickel into this 001 plane. But, well, the general conclusion would be that, well, we have quantitative good agreement between our calculation and the experiment. And, well, this indicates that, well, vanadium is a conventional and correlated Fermi liquid. Similar results we had in the description of nickel. This is, on this row are the experimental data. On this row are the already folded back by LCV procedures. The points into the Brillouin zone are the theoretical approach using the DMFT. And here is the LSDA approach. And here we try to see also differences by changing this Hund parameters, this J, but here we didn't have too much to see. And by this calculation we see that, well, in this asymmetry points, gamma, X, and L, you will see that increasing these Hubbard terms, so these points, in these points there are important changes into the to the Akar spectra. So going from gamma to gamma, there are changes, and also in this L points. We also wanted to make a square fit analysis for the value of the Hubbard U term we used, and well, by this least square fit analysis, we got the best agreement between experiment and the theory for this Hubbard U 2.0. But well, our general conclusion is that electron correlation in nickel leads to an isotropic contribution to the momentum distribution. Okay, so I will stop at this point, and I will try to sketch some general conclusions. So first of it, I would say that, well, Compton scattering and positron annihilation spectroscopy, as they map the ground states of the sample, they are used to check a theoretical model of solids. They are used to identify the electron correlation effects and to extract the Fermi surface topology. And in particular, the conclusion we had for the work for the magnetic Compton in iron nickel, spin density localization, anisotropy of the Compton profiles, and the positron annihilation spectra, I stressed at each point. Okay, I would like to thank you for your attention, and it was, how to say, nice to see you in person here. And what's new? So I was preparing actually a calculation. Guys, stop. Sorry. Okay, I didn't want to start it because my information was that, well, we will have also tutorials, but at this point it's not appropriate because you didn't have, how to say, first tutorial in order to use the SPR KKR method. But if somebody is interested, and I would be glad to found somebody, I could either send this tutorial or maybe it's available online if somebody wants to see it, or maybe they could address Sergey or Svetlana to show you how to do this calculation. So thank you once more for your attention.
So questions?
Yeah.
It's not going to work anyway. Well, basically, I wanted to ask. There was seen that introducing these correlations, you see some visible effects in the calculations, and mostly they led to better agreement with experiment. However, I wonder if it is possible to draw some kind of general conclusions. Let me, for instance, what was interesting for me, that for the nickel, when dealing with this Compton profile, in your results it was seen that there is a difference between static correlations, LA plus U and LA plus DFT, but only for, let's say, larger value of U. I just wonder why, or if one can say have some explanation why say this difference between LSD plus U and LSD plus DFT should be seen only for larger U, or if one can draw some general conclusions. Also, in the last case, with this annihilation experiment, there was a case that introducing U actually spoils the agreement with the experiment if it's done in the static way. So, just
well, depends much. So okay. So with this U, you can find all the time, how to say, best values, I mean, to describe either LSDA or DMFT. So you can do what we did with less square feet, with either with the LSDA plus U or with the LSDA plus DMFT, and maybe you would find different values of this. But so you don't, how to say, you cannot.
You mean to compare LSD plus U and LSD plus DMFT for the same value of U need not be always the proper?
Yeah, I would say so, but well, our general conclusion after working with this, well, it's then the description with the DMFT is better, gives better improvement in these profiles.
Yes, may I inquire about the uranium ion 2 calculations?
Yeah,
The moment you showed for the uranium,
yeah.
Is that coming from the uranium or it's an induced moment? Because the ion moments were pretty good in the LSDA, but the uranium moments were not very good. And usually that's a problem with sphere sizes or stuff like that.
Well, this is what some early work, so it's not, so it's an ASA, so I would not say so much, but yes, it's coming from uranium, so the value of the spin.
What's the crystal structure?
The crystal structure is lathes, is cubic lathes. So,
sorry, just one more question. The uranium ion has a lot of phases. Is that not possible that the experiment catches more than one phase?
this I'm not sure, but
The
as far,
lots of phases and they are very close.
yeah, well, we discuss it for this cubic lathes. We did at least the theoretical approach for these cubic lathes. I'm not sure if in experiment there is a mixed how to say sample.
Other questions? Nobody else? Okay, thank you again, Benea.